Okay, welcome back everyone. So, what products do we form in this reaction? First of all, you have to realize the two hydrogen atoms are now coming from the same side onto the double bond, right? That's the syn addition. That's very important. So now for the first possible products, the hydrogen, the metal surface with the hydrogen is coming from the back of the molecule. That means in this starting material, the ethyl group is pushed forward, and so is the methyl group, right? So the two hydrogens which came in from the H2, they're pointing backwards in this first product, and of course you can't see them because I have omitted them. They're implicit, right? And they're clearly pointing backwards because the other two substituents are pointing forward. Okay, so then the second possible product, which is the enantiomer of the first one, right? The hydrogen, the metal surface is coming from the front onto the double bond, and so that pushes the methyl substituent and the ethyl substituent to the back into the board. Okay, so we draw that with dashed lines. You see there are again these two possible products that clearly are enantiomers of each other, right? Each one has two chirality centers. So it is very important to realize here that two chirality centers are actually formed during the reaction, right? The starting material doesn't have any chirality centers, but the products they have, right? But only the stereoisomers, which result from syn addition, right? Where the hydrogen came from the same side, are actually formed here. Okay? Very, very important. You don't form all the possible stereoisomers. And these are very, very important things for the final exam. I'll be testing. So practice this concept, the syn addition of H2 with skill builder 5.5. Okay, in your book. So next, we are going to look at a different reaction. So we're going to look at so-called halogenation reactions next. And what happens in a halogenation reaction is we can do either chlorination or bromination. So we add either two chlorines or two bromines onto the double bond. And you have done such a reaction in a lab, right? We're kind of just reviewing what you've already learned. So, halogenation, again, that means addition of two halogen atoms across the carbon-carbon double bond. And, okay, give you some time to write it. Sorry. So here's what happens, right? So we have a carbon-carbon double bond. For example, here we're going to add two chlorine atoms starting from just simple chlorine, Cl2, and each chlorine atom adds to one side of the double bond. So that's what we get. Usually these reactions with chlorine and bromine are very high yielding. So in this case we get about 97% yield with just chlorinating ethylene. Alright, so far so good. Now a couple of notes of caution here. First, halogenation is really only practical with chlorine and with bromine. Important point, right? So what happens with other halogens? With iodine, essentially, iodine forms very weak bonds, weak carbon-iodine bonds, right? And so this is why with iodine there's not enough thermodynamic driving force to actually do this kind of halogenation reaction with a double bond. And so with iodine, the reaction just does not go. Very, very poor yields are obtained. So don't do this with iodine. What happens with fluorine? It happens the opposite. Carbon-fluorine bonds are extremely strong. And so if you add F2, which is very hard to handle anyway, it's a gas, super toxic, essentially a super violent reaction happens, which pretty much burns up your molecule. It's like, so you can't control the reaction well with fluorine. So people only do it with chlorine and bromine, not with iodine and not with fluorine. And the mechanism of the reaction is actually remarkably similar to the mechanism of the mercuration reaction we have already discussed. So we're going to look at the mechanism next in detail. Starting off, in this case with a cyclic alkene. I'm drawing a cyclic alkenes for these mechanisms because I think it helps you understand the stereochemistry better than if I use a flat alkene. And we're drawing this starting material in a so-called Haworth projection, which kind of makes it easier to see what's going on, again, in terms of stereochemistry here. So we start off with the alkene, put a bromine on top, and the Br2, and this is how Br2 gets oriented. One bromine points toward the alkene, the other points away from it. Right? Of course, the bromine can come in from either the top side or from the bottom side. In this case, these two approaches of bromine from the top or from the bottom are equivalent, right? Because as we'll see in a second, because this compound does not then form any chirality centers at the beginning. So now the bromine is actually polarized. You see, bromine Br minus can be a good leaving group, right? And so that means the electrons fluctuate. Sometimes that bromine bond gets elongated, and one of the two bromines kind of pulls away all the electrons and makes the other bromine have a delta plus. Okay, and so here's the arrow pushing now, which happens. The double bond is again the nucleophile, like we have always seen in these addition reactions. So you start the arrow in the middle of the double bond, right? So the electrons are coming from. You attack the nearby bromine. That's the electrophile. So Br2 can be an electrophile. That's important to realize. And that's because, again, Br minus then is the leaving group, right? And then what happens is, see again on the left carbon down there, of the double bond, you make a kind of transient carbocation when you start using the double bond as a nucleophile and attacking the Br2, and that means now one of the lone pairs, kind of like what we had happened when we formed the mercurinium ion, one of the lone pairs of bromine is attacking the double bond, again as a nucleophile. And so that forms a so-called bromonium ion. Okay, that's how we draw it. It's a three-membered ring structure which has a positive charge on the bromine, called again a bromonium ion. Of course, the other thing we form in the reaction is Br minus, right? So now the Br minus is able now to attack the bromonium ion from the backside. This is basically just an SN2 reaction where the bromine, the positively charged bromine, is the leaving group, and of course it's a great leaving group, right? It's an even better leaving group than Br minus. So what we form is, you see, the bromine, the Br minus, like in every SN2 reaction, has to attack from the back side. Okay, and so that means the bromines end up on opposite side in the end of the double bond, and we of course form the enantiomer here as well. The key question for you guys is, how does the enantiomer form? Kyle Chiatia should be able to show you that. Essentially what happens is the Br minus, to form the other enantiomer, will attack the left carbon atom instead of the right in the ring. Okay, so I will wait a few minutes and have Kyle show you how we form the other enantiomer. But first, a couple more notes here. The bromonium ion intermediate is actually really similar. Right? Remember that it's similar to the intermediate obtained for mercuration. Right, which we discussed a while back. Again, giving you a couple seconds here to write. Now, the other thing, the important thing to remember is the Br minus attacks the backside of the bromonium ion. That leads to exclusive so-called anti-addition. right, where the two bromines end up on opposite sides of the double bond. Speeding it up a little bit here. It's kind of slow. Okay, but I know you need some time to write it as well. All right, I will have Kyle explain to you how we can get the enantiomer in this process. I will meet back on the board, and I will meet back in a couple minutes. Thank you.